Hey everybody, this is Larry. This is me doing day 17, I think, of the Leetcode Daily Challenge. If it ever wants to load, it'll be nice. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, whatever it happens to be. What is going on with my internet? Is it working? Hello, hello, hello. There we go, day 17. Yeah, hope everyone's doing okay. I'm a little bit later today. So I apologize for that. I am in the. I'm right now in Kuala Lumpur. In Malaysia, it is very hot here. It's very sweaty. I need to do laundry. Yeah, I probably should. I was gonna do it today, but maybe it's a little bit disoriented. But I'll post some drone videos, or just videos in general, and you let me know what you think. But yeah, today's problem is 1361. Validate binary tree nodes. You have n binary tree nodes, numbers from 0 to n minus 1, where node sub I has two children left of child sub I and right sub child sub I. Return true if only all the given nodes from exactly one valid binary tree. What does that mean? If node I is okay, so you have this is a tree. This is true because it's a what? Binary tree node? It's not a binary search tree. Right? What is it asking? If all the given nodes form exactly one valid. Oh, I see. Oops. Let me try to think. What properties do we need to know, right? Maybe a minimal set, but we don't necessarily need to care about a minimal set. Just anything that gives us the answer, right? I guess there are a couple of things. One is that it's connected, so we have to do a depth first search at some point to make sure it's connected. I guess we can just do like a sort of a topological sort, but not really. We just try to, so there should be only one node that has no incoming node, and then we do a depth first search from that, and if we could see all the nodes, then we should be good. We just have to make sure that we don't visit the same node multiple times, like in example 2. And also, we have to be careful that we don't do duplicate work, I suppose. And what I mean by that is that, like, if you have, like, so let's say example 2 is a diamond. If we have multiple diamonds and you just kind of be lazy on the depth first search, or just recursion, I suppose, or backtracking. If you're lazy on the backtracking, it'll be like, 2 to the n very quickly. So we have to be careful about that, but I think that should be good enough, right? And even in that case, you can probably early termination, because the only way that it branches out is if it has multiple. So yeah, I think that should be fine. So let's do it, fellas. Man, my eyes are kind of tired. I didn't sleep that well yesterday. Jet laggy things. Yeah, Larry is old, or just jet lag, or my body's messed up. I don't know. Anyway, yeah. So let's just say in degree is equal to right. So for x in let's say left child plus right child maybe, right? And both. If x is not -1, in degree of x we just increment by 1. That means that we have a parent pointing to it. And then now we say for enumerate ix and enumerate in degree, right? If, or maybe we do it in a function just to kind of make it slightly easier. Get root, right? So if x is equal to 0, that means that there's nothing pointing to it. Then we can we return early? I guess you could do it in a number of ways. I was thinking that if multiple roots, that means that that's already not a tree. Yeah, right. So that's definitely no bueno. But yeah. But in that case, then you wouldn't return all the nodes. I think that's probably fine. return -1, right? Root is equal to get root. If root equals -1, then that means that we can't find a root, and then we return false. Otherwise, we can find a root, and then we can see if we visit every ring once, right? So scene, is it this one? Right? So for or yeah, just recurse on x, right? Yeah, then recurse left child of x, recurse right child of x. We have to do some work processing, of course, but yeah. So then maybe if x is in scene, we return false. Yeah, we return. Yeah, okay, fine. If not, this is really awkward, right? But okay, fine. So we visit the same node twice. Is that? I wonder if it's good enough to just kind of do it this way, and then now we can say that there are edges. Because what I want to say is that there should be the number of edges is equal to the number of node -1, right? If it's a tree. So I don't know if that's sufficient. But yeah, so then here we do a scene, right? So if length of scene is equal to or not equal to n, we return false. Obviously, we just insert the node, right? If I'll also say even before we do this, and we have to do recurse on root, we can even probably write something like if edges is not equal to length n -1, then return false, right? Is this sufficient? I know there's some stuff that you can do with cycle finding and stuff, but I'm trying to think whether this is enough. Because in this case, then we have 2 edges and 2 nodes, so that's going to be too much anyway, right? Let's just run it real quick. See if, well, this is, yeah, we need to do scene.add of x, right? That makes it a little bit easier. We messed up on this one. I returned false. Why do I return false? Oh, because yeah, if x is equal to -1, we return. I guess that's because it's doing some funky things on here. That's sloppy. Is this sufficient? I'm trying to think, to be honest. I know that that you can kind of write another set of things. I wonder if this is encompassing enough. All right, let me just give it a submit. If I forget something, we learn something. All right, looks good. 1295, much faster than my last time. What did I do last time? Yeah, I guess the in degree stuff. We find the root. And we see every node. Okay. I mean, I guess I did the same logic, but I don't know why this is so much slower necessarily. I guess maybe this kind of early termination helps cheat some test cases, but which is probably true, to be honest. I think oh yeah, I didn't go over the complexity, so yeah, let's go over that. I mean, this is linear, obviously. We just pass through the left and the right. The recursion is also linear, maybe also obviously, right? This just goes through the loop. This is the recursion, and this is also reverse linear because every edge we look at most once. And because of this scene, we make sure that we don't kind of get stuck in loops. And yeah, and that's it. So linear time, linear space because of the stack situation. Where's the stack? Oh, the recursion stack. So yeah, let me know what you think. That's all I have. Stay good, stay healthy to good mental health. I'm going to take a nap. I'll see y'all later and take care. Bye-bye.